Welcome to this coding walkthrough. In this session, we'll tackle the problem number 870, titled Advantage Shuffle. This problem is an interesting challenge that combines sorting and strategic decision-making. Stick around as we explore its solution step by step. The problem is called Advantage Shuffle. You are given two integer arrays, nums1 and nums2, both of the same length, n. The goal is to rearrange the elements in nums1 to maximize its advantage relative to nums2. Here, an element from nums1 is said to have an advantage over an element from nums2 if it is strictly greater. Your task is to return any valid permutation of nums1 that achieves this goal of maximizing the advantage. For the input, you will receive two integer arrays of equal length, nums1 and nums2. The output should be an array that is a permutation of nums1. This arrangement should ensure that the advantage relative to nums2 is maximized. Let's see some examples to understand this better. In the first example, we are given nums1 as 2, 7, 11, 15, and nums2 as 1, 10, 4, 11. The output is 2, 11, 7, 15. Looking at this arrangement, we compare each element in nums1 with the corresponding element in nums2. For the first pair, 2, 1, which gives an advantage. For the second pair, 11, 10, another advantage. For the third pair, 7, 4, another advantage. This rearrangement of nums1 ensures that all three pairs provide an advantage, maximizing it relative to nums2. Now, continuing with the first example, the last pair is 15, 11, which also provides an advantage. This completes the explanation for the first example, where all pairs yield an advantage. In the second example, nums1 is 12, 24, 8, 32, and nums2 is 13, 25, 32, 11. The output is 24, 32, 8, 12. Let's analyze this arrangement. For the first pair, 24, 13, which gives an advantage. For the second pair, 32, 25, another advantage. For the third pair in the second example, 8, 32, so there is no advantage here. However, for the fourth pair, 12, 11, which provides an advantage again. This arrangement maximizes the advantage relative to nums2. In the third example, nums1 is 5, 5, 5, 5, and nums2 is 6, 6, 6, 6. The output is 5, 5, 5, 5. Since no element in nums1 is greater than any element in nums2, there is no way to achieve an advantage. In the third example, comparing the elements of nums1 with nums2, we see that no pair satisfies the condition of nums1, I, nums2, j. Therefore, no advantage can be achieved. Let's now consider the constraints. The length of the arrays, n, can be as large as 100,000. The values of the elements in both arrays can range from 0 to 1 billion. Since nums1 and nums2 always have the same length, we must work efficiently to handle large input sizes. Sorting-based approaches with a time complexity of O(n) log n are well suited for this problem. Additionally, it's important to consider edge cases, such as when all elements in nums1 are identical or when nums1 and nums2 are identical. In such cases, any permutation of nums1 can be valid, as no specific advantage can be achieved. These constraints and edge cases highlight the importance of designing an efficient and flexible solution. To start, let's consider the brute force approach to solving the advantage shuffle problem. The idea here is to generate all possible permutations of nums1 and evaluate each one to determine which maximizes the number of positions where nums1, I, is greater than nums2, I. For each permutation, we compare corresponding elements of nums1 and nums2, counting how many positions satisfy this condition. The permutation that gives the highest count is chosen as the result. While this approach is straightforward and easy to understand, it is computationally expensive. Generating all permutations of nums1 involves factorial time complexity, O(n), and for each permutation, comparing it with nums2 requires O(n), leading to an overall complexity of O(n). (n). Additionally, storing intermediate permutations demands O(n) space. These trade-offs make the brute force approach impractical for larger input sizes. Now, to address this inefficiency, we can adopt a greedy strategy that focuses on maximizing the advantage more systematically. The greedy approach optimizes the solution by taking advantage of a key insight: we don't need to focus on beating every element in nums2 directly. Instead, we can strategically allocate numbers from nums1 to maximize the overall advantage while minimizing losses. Here's how it works. First, sort both nums1 and nums2, and for nums2, we also store the original indices by creating an array of tuples. Then, we use two pointers, one to track the smallest remaining number in nums1 and another for the smallest remaining number in nums2. If the smallest unused number in nums1 can beat the smallest number in nums2, we assign it to do so. Otherwise, we assign the smallest number in nums1 to lose gracefully against the largest remaining number in nums2. Finally, we reconstruct the result array by placing the assigned numbers in their original positions based on the indices stored earlier. This approach has a time complexity of O(n) log n, due to sorting in a linear pass with the two pointers, and it uses O(n) additional space for storing the mappings. It's efficient, guarantees an optimal solution, and avoids the impracticality of the brute force method. Given the trade-offs of the two approaches, the greedy strategy stands out as the most practical and efficient solution for this problem. While the brute force approach is conceptually simple, it is computationally prohibitive for larger input sizes due to its factorial complexity. The greedy method, on the other hand, achieves the desired result in O(n) log n time, making it scalable and robust. The core insight here is realizing that not every element in nums1 needs to directly beat an element in nums2. Instead, the goal is to maximize the overall advantage by strategically assigning values. This approach strikes a balance between computational efficiency and correctness, leveraging sorting and two-pointer traversal to solve the problem optimally. While it does require additional space to maintain the mapping of indices, this cost is negligible compared to the performance benefits. In summary, the greedy approach is the clear choice for its scalability, clarity, and ability to handle large inputs effectively. The advantage shuffle problem challenges us to rearrange elements in one array, nums1, so we can maximize the number of indices where nums1 I is greater than nums2 I. To achieve this, we'll use a greedy algorithm. First, we sort nums1 in ascending order, making it easier to find the smallest element that can beat a given value in nums2. Next, we create an array called indexed_nums2, where each element is paired with its original index from nums2. This step ensures that, even after sorting nums2, we can match results back to their correct positions. Sorting both nums1 and indexed_nums2 allows us to efficiently apply the greedy strategy, focusing on pairing the smallest elements first to maximize the advantage. Now, we implement the core of the algorithm using a two-pointer approach. We set one pointer, left, at the beginning of the sorted nums1 array, and another pointer, right, at the end. We also prepare an empty result array of the same size as nums1, which will store the rearranged elements. As we iterate over indexed_nums2, we handle each value based on whether nums1, left, can beat it. If nums1, left, is greater than the current value in nums2, we assign nums1, left, to the corresponding index in the result array and move the left pointer forward. If it cannot, we assign nums1, right, to the result, effectively sacrificing the largest remaining element that cannot win, and move the right pointer backward. This strategy ensures that we maximize our advantage where possible while minimizing losses. After processing all elements in indexed_nums2, the result array will contain the rearranged nums1 values that maximize the advantage. The greedy strategy here is key. It ensures that we always use the smallest available element in nums1 that can win, while preserving larger elements for tougher matches. When no winning element is available, we sacrifice the largest remaining value, which is least useful for future pairings. Sorting nums1 and indexed_nums2 upfront enables efficient pairing, and the two-pointer technique minimizes time complexity while maintaining the algorithm's effectiveness. We also use an indexed array to track nums2's original positions, ensuring our final result respects the input structure. This combination of sorting, the two-pointer approach, and greedy pairing ensures an optimal solution. The algorithm's efficiency lies in its time and space complexity. Sorting nums1 and indexed_nums2 each takes O(n) log n, and the pairing process with two pointers runs in O(n), resulting in an overall time complexity of O(n) log n. Space complexity is O(n), as we use additional arrays for indexed_nums2 in the result. Let's see an example. Suppose nums1 is 12, 24, 8, 32, and nums2 is 13, 25, 32, 11. First, we sort nums1 into 8, 12, 24, 32, and indexed _nums2 into 11, 3, 13, 0, 25, 1, 32, 2. Using the two-pointer approach, we pair each element, 8 beats 11, 12 beats 13, 24 beats 25, and 32 is sacrificed against 32. This step-by-step pairing ensures we maximize the advantage while respecting nums2's original order. Finally, the result array is 24, 32, 8, 12, which maximizes the advantage. Specifically, 24 beats 13, 32 beats 25, and 8 beats 11, while the last pairing sacrifices 12 against 32. By following this greedy approach, we ensure that nums1 is rearranged optimally to win as many pairings as possible. This solution demonstrates the power of combining sorting, two-pointer techniques, and greedy strategies to tackle challenging optimization problems efficiently. The problem advantage shuffle involves reordering elements of nums1 to maximize the number of positions where nums1 I, nums2 I. The greedy approach ensures optimal results efficiently. First, nums1 is sorted in ascending order. This allows us to easily access both the smallest and largest values. Next, we pair each element in nums2 with its original index and sort these pairs by the values in nums2. This helps us to determine the smallest value of nums2 that needs to be beaten while preserving the original order of nums2. We initialize an array, result, of the same length as nums2, filled with placeholders, -1. This array will store the final rearranged nums1 values. Two pointers are used to traverse nums1, low starts at the smallest value, and high starts at the largest value. For each element in the sorted nums2, if the smallest value in nums1, pointed by low, can beat the current nums2 value, we place it in the corresponding position in result. Otherwise, we use the largest value in nums1, pointed by high, to avoid wasting small values that cannot beat nums2. After iterating through all elements, the result array contains the rearranged nums1 values that maximize the advantage. This approach has a time complexity of O(n log n) due to sorting, making it efficient for large input sizes. Here, we start by implementing the advantage shuffle problem in Java. First, we sort the nums1 array in ascending order to make it easier to select the smallest or largest values as needed. Then, we create an auxiliary array called index nums2, which stores both the values of nums2 and their original indices. This is important because the final result array needs to maintain the relative positions of nums2. We populate this array by iterating through nums2 and storing each value along with its index. Next, we sort the index nums2 array based on the values of nums2, ensuring that we can process the smallest elements of nums2 in order. After that, we initialize a result array to store our final output and set up two pointers, low and high, to traverse through nums1. These pointers will help us decide whether to use the smallest or largest available value from nums1 for each element in nums2. Now, we start iterating over the sorted index nums2 array to determine the best matches for nums1 and nums2. When traversing the sorted index nums2 array, we check if the smallest in used value in nums1, pointed to by low, is greater than the current value in nums2. If so, we use this value from nums1 to maximize the advantage and place it in the result array at the original index of the current nums2 element. Then, we increment the low pointer to move to the next smallest value. However, if the smallest value in nums1 cannot beat the current nums2 value, we instead use the largest available value in nums1, pointed to by high, to minimize the loss. This ensures we save the more advantageous values for later comparisons. The high pointer is then decrement to move to the next largest value. Once the loop completes, the result array contains the optimal arrangement of nums1 elements that maximizes the advantage over nums2. Finally, we return the result array as the output. Here, we start with the first example where nums1 is 2, 7, 11, 15, and nums2 is 1, 10, 4, 11. The first step is to sort nums1 in ascending order, which gives us 2, 7, 11, 15. Next, we pair each value in nums2 with its corresponding index, resulting in 0, 1, 1, 10, 2, 4, 3, 11. Sorting this list by the values of nums2 gives us 0, 1, 2, 4, 1, 10, 3, 11. At this point, we initialize the result array as -1, -1, -1, -1, and set up two pointers, low at 0 and high at 3, which represent the smallest and largest values in nums1, respectively. Now, we begin traversing the sorted indexed underscore nums2. For the first pair, 0, 1, the smallest value in nums1, 2, is greater than 1, so we assign result, 0, equals 2 and increment the low pointer to 1. Next, 4, 2, 4, nums1, low, is now 7, which is greater than 4, so we assign result, 2, equals 7 and move low to 2. 4, 1, 10, nums1, low, is 11, which is greater than 10, so we assign result, 1, equals 11 and move low to 3. Finally, 4, 3, 11, nums1, low, is 15, greater than 11, so we assign result, 3, equals 15 and increment low to 4. The final output is 2, 11, 7, 15. In the second example, nums1 is 12, 24, 8, 32, and nums2 is 13, 25, 32, 11. First, we sort nums1 to get 8, 12, 24, 32. Then, we pair nums2 with its indices, resulting in 0, 13, 1, 25, 2, 32, 3, 11, and sort this by the values in nums2, giving us 3, 11, 0, 13, 1, 25, 2, 32. We initialize result as -1, -1, -1, -1, and set the low pointer to 0 and high pointer to 3. Now, we process each pair in indexed underscore nums2. For 3, 11, nums1, low, is 8, which is less than 11, so we assign result, 3, equals nums1, high, which is 32, and decrement high to 2. For 0, 13, nums1, low, is 12, which is less than 13, so we assign result, 0, equals nums1, low, which is 12, and increment low to 1. For 1, 25, nums1, low, is 24, which is less than 25, so we assign result, 1, equals nums1, high, which is 24, and increment low to 2. Finally, 4, 2, 32, nums1, low, is 8, so we assign result, 2, equals nums1, low, which is 8, and increment low to 3. The final output becomes 32, 24, 8, 12. In the third example, nums1 is 1, 2, 3, 4, and nums2 is 2, 2, 2, 2. First, we sort nums1 to get 1, 2, 3, 4. For nums2, pairing with indices gives 0, 2, 1, 2, 2, 2, 3, 2, which is already sorted. We then initialize result as -1, -1, -1, -1, and set the low pointer to 0 and high pointer to 3. Now, we evaluate each pair in indexed underscore nums2. For 0, 2, nums1, low, is 1, which is less than 2. Therefore, we assign result, 0, equals nums1, high, which is 4, and decrement high to 2. For 1, 2, nums1, low, is still 1, less than 2, so we assign result, 1, equals nums1, high, which is 3, and decrement high to 1. For 2, 2, nums1, low, is still 1, less than 2, so we assign result, 2, equals nums1, high, which is 2, and decrement high to 0. Finally, 4, 3, 2, we assign result, 3, equals nums1, low, which is 1, and increment low to 4. The final output is 4, 3, 2, 1. The time complexity of the advantage count algorithm can be explained in 3 main steps. First, we sort the nums1 array, which takes O, n log n, since sorting is performed on an array of size n. Next, we create a list of pairs from nums2 by combining its elements with their indices using the enumerate function. Sorting this indexed version of nums2 also takes O, n log n. Finally, we use a two-pointer approach to assign elements from the sorted nums1 to the appropriate positions, based on the sorted order of nums2. This traversal involves iterating over the n elements in nums2 and performing constant time operations for comparisons and assignments, leading to an O, n, complexity for this step. When we sum these contributions, the overall time complexity becomes O, n log n, plus O, n log n, plus O, n, which simplifies to O, n log n. Now, let's explore the best, average, and worst-case scenarios. Regardless of the input distribution, whether nums1 or nums2 is sorted or random, the sorting steps dominate the runtime, and their complexity remains O, n log n, in all cases. Moving on to the space complexity, we can break it down as follows. Sorting nums1 is done in place, which means it does not require any additional memory, contributing O1 extra space. However, we do create the indexed underscore nums2 list, which stores n pairs of index value combinations derived from nums2, consuming O(n) space. Additionally, we allocate the result array to store the final output, which also requires O(n) space. These components together constitute the space complexity of the algorithm. If we total the space usage, we find that the algorithm requires O(n) space for the indexed _nums2 list and another O(n) for the result array. Therefore, the overall space complexity is O(n). Importantly, the algorithm avoids using any additional data structures or recursive calls, so no extra space is consumed beyond these two arrays. Let's compare this approach to the brute force method. In the naive solution, we would iterate through each element of nums1 and compare it with every element of nums2 to find the smallest valid match. This nested iteration results in a time complexity of O(n squared). By contrast, the optimized solution leverages sorting and the two-pointer technique to achieve a time complexity of O(n log n). Both approaches have a space complexity of O(n), primarily due to the result storage requirement. Finally, let's solidify our understanding with some reasoning based on big O notation. The sorting operations are the most computationally expensive part of the algorithm, and Python's timsort guarantees a time complexity of O(n log n for each sort. The linear traversal step, which assigns results using the two-pointer approach, adds an O(n) contribution. When we combine these, the overall time complexity remains O(n log n). On the space side, the auxiliary arrays indexed _nums2 and result each require space proportional to the input size, resulting in O(n) space usage. This efficient use of time and space makes the current solution far superior to the brute force approach, particularly for larger input sizes, while still maintaining linear space requirements. When tackling the advantage shuffle problem, there are some common mistakes to watch out for. First, overlooking edge cases can lead to major issues. For instance, if you don't handle empty input arrays or scenarios where all elements are equal, your solution might crash or produce incorrect results. Always ensure your code explicitly handles these situations. Another common mistake is misunderstanding the problem's requirements. Remember, the goal isn't to preserve the order of elements in nums1, it's about maximizing the number of elements in nums1 that are greater than their counterparts in nums2. Misinterpreting this can lead to invalid solutions. Additionally, some people use brute force approaches like generating all permutations of nums1, which is computationally expensive given its factorial time complexity. Instead, sorting combined with a two-pointer approach is much more efficient. Finally, be mindful of sorting stability. If the problem involves custom sorting, unstable sorting can disrupt the relative order of equal elements, leading to unintended behavior. Stable sorting ensures consistency and helps avoid subtle bugs in these scenarios. Another inefficiency to avoid is comparing every element of nums1 with every element of nums2 in a nested loop. This results in O(n squared) time complexity, which is suboptimal for larger inputs. Instead, a two-pointer strategy is much more efficient. This brings us to an important insight: sorting both nums1 and nums2 enables the systematic assignment of elements without backtracking. This strategy avoids unnecessary comparisons and reduces the problem's complexity. However, sorting the arrays does come with a trade-off: it has a time complexity of O(n log n). That said, this is far more efficient than the factorial complexity of brute force approaches, making it a critical optimization for larger datasets. Interviewers often look to see how you transition from brute force to an optimized solution like this, so be prepared to explain why a two-pointer strategy is better and how it aligns with the problem's requirements. To solve the problem effectively, focus on a greedy strategy: assign the smallest possible element in nums1 that is greater than the current element in nums2. For elements in nums1 that can't counter anything in nums2, set them aside in a remaining elements list to use later. The advantage shuffle problem shares similarities with other challenges in algorithmic problem solving, which can help you build a broader understanding. For instance, problems like LeetCode 406, queue reconstruction by height, or LeetCode 881, boats to save people, also require sorting and strategic pairing. Another related problem is LeetCode 942, DI string match, which also involves leveraging greedy algorithms. Exploring these will deepen your grasp of patterns like sorting and two-pointer strategies. Now, let's consider alternative approaches to solving the advantage shuffle problem. The brute force method involves generating all permutations of nums1 and evaluating each to find the one that maximizes the advantage. While conceptually simple, this approach is computationally expensive with a time complexity of O(n). For larger arrays, it becomes infeasible. On the other hand, the sorting in two-pointer approach is far more practical. By sorting both arrays and systematically pairing elements, you can achieve an optimal solution with a time complexity of O(n log n). This method is efficient and well-suited for most input sizes, making it a preferred choice in interviews and real-world applications. An alternative to the two-pointer approach is the binary search method, which uses a sorted data structure like a tree set or applies binary search to find the smallest element in nums1 that is greater than the current element in nums2. This approach has a time complexity of O(n log n, similar to the sorting in two-pointer method, but it introduces slightly more complexity in implementation. For instance, maintaining a sorted dataset dynamically can be challenging, especially when elements need to be added or removed frequently. However, this method works particularly well with balanced binary search trees, which ensure efficient lookups and updates. While it's less commonly used than the two-pointer strategy, it's a great alternative for cases where dynamic operations are required or when the problem constraints align better with binary search. Understanding these different approaches allows you to choose the most suitable one based on the problem's specific requirements and constraints. Great job making it to the end. Today, we covered the advantage shuffled problem and explored how sorting in a greedy approach can simplify this challenge. Remember to practice similar problems to solidify your understanding. Thanks for watching, and don't forget to like and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!